In this section, we're going to be discussing the initialization of the firmware to deal with digital control of the buck converter, specifically with the STM32 G474RE, the nuclear board to be more specific. So to get started, the initialization is actually going to be done using the CubeMX. Of course, this can be done bare metal, but in this particular case, it's much easier to use the CubeMX that's already made available. So first up, I'm gonna open the STM32 CubeMX, and yeah. So the first thing to do after opening the CubeMX is of course new project. It's going to open a new project, and you want to go to the board selector. Then once you go to the board selector, you want to select the commercial part number. For this example, I'm actually utilizing the Nucleo G474RE. So that's what I'm going to go for. So after that, it's already been selected. You click on that, and then you start the project. And then it says initialize all peripherals at the default mode. I would say yes to that, and it's gonna load the IOC. Just waiting for it to load. Okay, so the first thing you want to do is go to the clock configuration. Just ensure. Okay, so for this particular board that I'm utilizing, the maximum clock frequency is of course 170 megahertz. Of course, you can adjust it here. You can put some prescalers over there to reduce the clock speed. But in this case, I sort of want maximum PWM resolution to realize closed loop control. It's easier that way. I have more resolution in like the voltage that I can select. It's more finer, the resolution. So I'd rather just have it at the maximum clock frequency. So this is just perfect. So I go to the project manager, and the first thing you want to do is you want to copy your path where you want to put it, and you want to paste that there. And then you want to name this. So in this case, I'm going to name this project buck control. And then once you have that, you need to change the tool chain, the IDE. This is going to be STM32 Cube IDE. That's very important, of course. Yeah, and that's about it. I just want to make sure I'm not missing anything here. And that's about it on this branch. You've already chosen the project name, the path, and what you want it to be generated in, where you're actually going to implement the firmware in. And the tools, that's not necessary. Nothing has to be changed over there. And the pinout and configuration. So in this particular video, we're going to be discussing the initialization of the peripherals that you actually need to realize this closed loop control. So I will not be concerning myself with a lot of other peripherals. The STM32 is a microcontroller that's very capable. It's capable of a lot of tasks, and I sort of don't want to focus and dive too deep. It gets quite confusing at times. So the purpose of this video is sort of just to initialize what is actually needed to realize this system. Basically just the initializations are going to be completed here. So we're going to start with the system core. You're going to go to the DMA, and before I actually do the DMA is actually going to be used in conjunction with the ADC. So with analog to digital converters, there's several ways you can actually. So once you do the analog to digital conversion, you actually have to retrieve the result of what has been converted, of the conversion basically, and you can do that in several ways. The most by far, I think the most convenient way for closed loop control is to use the DMA, and I'm going to show you how and why. in shortly. And basically, maybe not in this section, in the next section, but the method chosen here is the DMA. So in this case, we're going to be utilizing two ADC channels, one ADC, just one ADC, ADC1, but two channels of it. So that's what you want to do here. You click on ADC, just go back, click on ADC over there, and then you IN1, which is channel one, IN1 single-ended. It's not going to be differential in this case. IN2 single-ended as well. And then after you do that, you sort of, before you carry on with the initialization of the rest of the ADC, you want to sort of go back to the DMA and you want to add to it. You want to click on add over there. You want to select, and you're going to select the ADC1. And once you do that, you go to the mode, you go to the circular mode, and then here you want to choose the word. Here as well, you want to choose the word over there. Data width. And that's about it. That's basically all you need to do for the DMA. I reiterate, you want to choose the circular mode, and the data width, you want to make sure it's word for both of them. And that's that. My focus in this video is not to go too deep into any of the peripherals. It's important that when you want to implement something as such as a closed loop control, I sort of want this to be as in essence as simple as possible, easier to digest, because I believe to sort of go deeper into firmware and coding it, you need to master basics first and then go deeper from there. So I sort of just want to do it on a basic front in this video, initializing from a perspective. So we went on a tangent there, but back to an ADC. So back to the ADC, what you want to do for the initialization in this case. So first off, in the ADC, it's in independent mode. The clock prescaler, you sort of want the ADC to be as fast as possible. Synchronous clock mode divided by 4. That's perfect. ADC resolution, of course, it should be noted that if you go for other types of resolution, you do get it will be much faster, just less accurate, and the data alignment is actually not necessary. It doesn't really matter in this case, because you're not taking it directly from the registers, so it doesn't matter. It comes already as it should. And then the scan conversion mode, it's disabled in this case because we haven't chosen both of them yet. But anyway, I carry on. So end of conversion selection, you want it to be end of sequence of conversions, because you're having two channels in this case. So continuous conversion mode, you want to enable that. Low power auto weights, you can just sort of leave that. I'm actually going to just focus on the stuff that you need to change, and the rest will just stay in the default mode as they should. And DMA continuous requests, because it's connected to the DMA, you want to continuously receive updates and conversion there. And then next, you want to say ADC regular conversion mode. Enable. Oversampling, that will not be necessary. So number of conversions, because you have two channels, you're actually going to select 2 in this case. So external trigger conversion source. External trigger conversion edge. So the ranks are as follows. So rank basically means this is IN1, and you want to select that to be channel 1. And then the next cycle, this is the number of cycles, the sampling time. I like to go for the maximum sampling time, because this actually makes sure that my readings are a lot stable, much stable. I mean, of course, you sacrifice time, but I'll sacrifice time any day if the readings are actually stable. So I go for the maximum there. And then rank 1 is completed, so you want to go to rank 2, and you want to select channel 2 in this case, and you want to go 640.5, same as the other one. And then after that, you sort of want to go back to scan conversion mode, and now you can actually okay, that's disable. Scan conversion mode, you actually want to enable that now. I remember before it was not, you couldn't enable that. But anyway, just a brief summary of the ADC. First off, of course, the DMA, I've discussed that already. So first off, you want to make this single-ended. IN2 single-ended, and then next. What you do is you go start from the top. What needs to be changed, basically, you want to focus on your top the resolution, 12-bit in this case, scan conversion mode. Keep in mind that this will not be enabled until you select the number of channels, the number of conversions that you actually want to execute. So this will be disabled, I believe, at first. And then what you want to do is you just want to skip that. Then you end of conversion selection, you want to select that to be the end of sequence of conversions. Continuous conversion mode, you want to enable that. DMA continuous request, you want to enable that as well. And then you want to enable regular conversions. Yes, you want to enable that. Next is the number of conversions. Is it going to be 1 or 2? In this case, you're going to select it to be 2. In this case, you want an external trigger conversion source. Actually, I do not want to focus on that. But in this case, just in case your specific development board does not have this selected, I think you just select it as regular conversion launched by software. And that's that. And of course, you have the ranks. Select channel 1 there. You want the maximum sampling time. For the rank 2, channel 2, maximum sampling time as well. And that's about it, actually. This enable injected conversion mode, you don't require that. Everything else essentially is gonna stay the same. There's no difference. And that's basically that for your ADC and your DMA. And now you're always gonna receive updates. So everything is done, nicely tied over there. And then the next part is actually the timers. So first up, I'm gonna go with timer 1, and this is specifically for the PWM. So you want to select your clock source to be internal clock, and the channel, you want to select that to PWM generation channel 1. You're not having interest in outputs in this case, so you sort of will just want to go with channel 1, not channel 1 in, where the polarity is actually inversed relative to channel 1, of course. But in this case, you want to just go with PWM generation channel 1, and as you select that, you should keep in mind where the channel actually is, PC0 in this case. Then after that, sort of want to go up there. Right. So after that, this is actually where you need to do some calculations, but I have equations already ready for this. The things that you have to change in this aspect are as follows, that you need to really pay attention to. The counter mode, it's up, in this case. Dithering, in this case, some of the microcontrollers don't actually have this, so you just ignore this. But the two major calculations that you values rather that you should worry about are the counter period and the prescaler. The internal clock division, of course, no division for maximum resolution, of course, and the auto reload preload. Yes, you want to enable that, and that's about it. You don't need to worry about the break dead time management. Of course, that would play a role into other aspects such as synchronous converters, synchronous buck, boost, whatever kind of converters. You would need to worry about dead time management in those aspects, and also with I think that's about it. Also half bridge converters. You sort of want to worry about that as well. But anyway, for now, what you really want to focus on are the prescaler and the counter period. And as you can see, it tells you this is 0 to 65535, and here it's the same 0 to 65525. But the equations that you should really worry about in this case are as follows. So I'm just gonna port this over here. So this is basically the equation for this. Let me just put that nicely in the middle. So this is the equation. This is the FPWM frequency. This is the frequency of the clock. The ARR value. The ARR value is equivalent to the compare value, and the prescaler value is of course that. So let me just close this for a second. Okay, so this is the auto reload register value, i.e. the ARR value, and this is the PSC value. So what I usually like to do is, in cases like this, I like to have it such as this, right? Where I have the ARR value, let me actually do that, because that other part is not necessary right now. So what I usually like to do is I like to assume a value for the prescaler and calculate a value for the ARR. So in this case, the prescaler value, I choose it to be 1. That's my first value that I choose it to be. And then I calculate the ARR value, the subsequent ARR value, and keep in mind the frequency of the PWM. So in this particular example, I want a PWM frequency of 100 kilohertz, and my frequency of the clock is the 170. So I have a calculator off screen that I'm utilizing for this. And when you actually do this calculation, you find that your ARR value that you calculate is actually 849 in this specific case. So it's again frequency of the clock, that's 170 megahertz. PSC, the prescaler, I choose it to be 1, and the frequency of the PWM that I desire is 100 kilohertz. Keep in mind when you type this into the calculator, you shouldn't say just 100. Assume this is not going to be in kilohertz. This is actually the frequency in hertz. Both of them are in hertz. By the way, if you want to make the frequency of the clock in kilohertz, make the frequency of the PWM also in kilohertz. Always keep the same units between these two. And of course, this is just a single value, which is just 1. And also, do not forget this right here. It's actually quite negligible, the effect it will have for an ARR value. If the ARR value is a lot greater than 1, then you don't need to worry about this. But just for the sake of proper design procedure, just keep that in mind, the -1. Anyway, when I calculated this on the calculator off screen, it's actually 849, the value. So I'm just gonna go there, the prescaler, I'm gonna make that 1, and the counter period, I'm gonna make that 849. All right, and that's about it. So this is a brief recap on it. So first off, you want to choose an internal clock as your clock source. Next, PWM generation, CH1, channel 1. And next, after that, the two things you need to focus on are the prescaler, which in this case I choose to be 1, and then I calculate the ARR using the following equation, which is this. That's what you need to, these are basically two values you need to worry about. And finally, auto preload, reload, you want to enable that. Oh, I disable that. You want to enable that. And then that's about it. That's about it for the PWM generation. Remember, this is strictly focusing on the initialization of these variables. And that's that. And then next is actually the timer interrupt. And keep in mind that in the previous code, I selected that to generate the digital coefficient, I actually selected that value to be the timer interrupt, the interrupt time to be 100 microseconds, which means the frequency is actually 10 kilohertz, which is 1 divided by 100, multiplied by 10 to the power minus 6, which is 100 microseconds. So anyway, I choose timer 4 in this case to implement the timer interrupt. So the first thing you do is you select the clock source. You say an internal clock, and we're not having any outputs in this case, so we don't need to select any channels in this case. And then the next thing, of course, as before, what you want to do is you revisit the same equation, slightly different this time. So this is the equation you use in this case. It's actually not different. I just changed the frequency of the interrupt, which in this case is 10 kilohertz. And the same procedure that was done before is followed here. You select the prescaler, which in this case is going to be 1. You select that prescaler, keep in mind your frequency of your clock, and then you have all the values and you can actually calculate the ARR. So off screen here, when I calculate this particular value, it's 8499. Also, again, keep in mind, just keep units constant. If you use kilohertz here, use kilohertz there as well. You don't want to sort of be making mistakes here, because this matters a lot. It's relating to the time. Anyway, that's that, and the ARR. I have the ARR and the prescaler value. I'm just gonna go back, punch it into the code. All right, so I have that there, and I have 8499, and that's about it. and that's all you need to do. Just to recap again on this, so for timer 4, you select the clock source of internal clock, and then next thing, you need to worry about two values again, prescaler and the ARR auto reload register. And once you select those two, so you choose this one, you choose what the prescaler is going to be, PSC value 1, choose that to be 1, and here you actually calculate the ARR, which I calculated off screen, which is 8499. All right, and that's about that. So just to recap, overall recap, I guess, on everything. What was done? The ADC was implemented, was initialized rather. So first off, you want to go to the ADC one, single-ended iron one, single-ended iron two, and the parts to take into account to initialize are basically the ADC resolution, end of sequence of conversion. You want to make sure it's off to everything. Um, and then once you go to ADC regular conversion mode, you want to make sure the number of conversions is 2. Of course, if you have 3, you make that 3, etc. And you want to take into account the ranks. Make sure the channel, this is channel 1, and the sampling time is as high as possible. Of course, you can go low. You should note that in this case, if you go too low, the ADC would actually not work. It won't convert properly. So that's just something to know from a practical standpoint, that the ADC simply just won't convert and you will not see the values. So from the DMA. So just keep that in mind. You sort of want to go on the higher side and reduce the speed as for your specific applications. But I suppose, for in some cases you sort of want to be much faster, but I would suggest going higher. So channel 2 sampling time, same thing for the rank number 2, and then you need to keep in mind enable regular conversions. That needs to be enabled, and then regular conversion launched by software. And where's the ADC? All right, continuous conversion modes, that's very important, and the DMA continuous requests, that's very important as well. Scan conversion mode, I already spoke about that. Also remember, you need to select 2 ranks before you're allowed to even enable this. And of course, the DMA continuous request, you will not be able to enable it until you've initialized the DMA, which, again, you just select that, ensure it's word, and mode is circular, and that's about it. And that is about it in short. The initialization of these the initialization of the peripherals that you require to implement the firmware for closed loop control of a buck converter. Well, that was a lot, but I just make sure I get everything in as to so that you understand exactly what you're doing and you're not confusing yourself and making errors, because it's yeah. I sort of look at it from when I started using STM, very confused on the aspects, and it's just, it's not necessary to be, it can be avoided, confusion can be avoided, which is what the goal of this is. Anyway, that's the initialization. The DMA is done, ADC is done, and the timers are done, both for the PWM generation and the interrupt. And that's that. And next you want to generate the code. So it's going to generate the user code and give you the option to actually open it up in the STM Cube IDE. Alright, so this option is to open the folder, open the project. I'd rather just open the project in STM Cube IDE, STM32 Cube IDE. And, it's gonna open up in this workspace, so yes, launch. And there it is. So it's actually so it successfully imported it. So we just open it up, go over there. All right, and there it is. So can go to the source, main function, and actually see all the peripherals that we initialized, which is the DMA, the ADC, timer 1, and timer 4. And that's about it. So yeah, this is basically initialization. And yeah, lastly, before I forget, let me just go back to CubeMX. I can just close that now. And to sort of maybe you missed something and you want to change something that you've initialized before, you just go to buck control and actually open buck control.ioc. You can actually open a perspective to actually see what you've done to actually reinitialize. No, I don't want to do that. So load in IOC. Okay, it's taking some time. All right, so that's basically it. And then here, perhaps you made a mistake. It's possible that the mistake might have been made, but anyway, that's basically what you need for the initialization. For this, that's what you need from scratch. Those are the things to take note of. And yeah, that's about it. So in the next section, we're obviously going to dive into code and firmware. There's several other aspects that need to be taken into account. It's not ready to be, of course, as you can imagine, not ready to be loaded into my controller. So in the next, we're going to get into the firmware, code and firmware. All right, I hope that has been of help to you in terms of initializing the peripherals that you require. Cheers. See you in the next one.